Hi everyone, this is Jeff from UT Austin, and today I'm going to talk about our work, Syntra, the synthesized cross-layer controllers for low-latency video streaming. Well, the pipeline of a low-latency video streaming is fairly complex. A video source will generate some frames, and then the system needs to decide, should we skip this frame? What bit rate should we compress this frame at? And how much FEC redundancy should we add? And how fast should we send packets into the network? Among them, ABR and CCA have been well studied. However, when combine them together, the problem is still pretty hard. We found that the state-of-the-art rate controller, WebRTC GCC, is slow to adapt to network changes. We run it on the link, alternating between 2 Mbps and 500 kbps every 40 seconds. When the link rate increases, the CCA wants small bytes to probe the network. However, the encoder cannot provide enough bytes. So this causes a slow ramp-up problem and takes about 20 seconds to convert to the new bandwidth. When the link rate decreases, the problem still persists. GCC will quickly detect that the bandwidth capacity drops and then notify the ABR. However, the ABR layer's encoder is unpredictable and cannot cut the output instantly. So this causes a latency spike, which is over 600 millisecond delay on bandwidth drop. And even at steady state, there's still a problem because the encoder's output is pretty unpredictable. So at best effort, what GCC can do is to leave headroom to buffer to absorb any unexpected burst. However, this conservative strategy causes 2 to 3 times waste in link utilization. Actually, there are many other interactions between the control actions and the objectives. For instance, FEC grouping creates a trade-off between latency and throughput. If you add FEC per frame, each frame can be decoded very quickly when there's a loss. So it is less likely to miss this deadline. But if you group FEC across several frames, you will get a higher throughput at the risk of missing deadlines. What's more, the controller needs to occasionally send above this current rate to estimate capacity, so adding FEC is needed to prevent frame loss. But it risks violating the latency bound. And when the bandwidth probe causes packet delay or loss, frame escaping becomes necessary to recover without blowing the latency budget for all future frames. For more interesting interactions, feel free to refer to our paper. So my advisor, which I think is a clever man, kept asking me over and over again, we cannot even design classical controller, so how can we design a cross-layer controller? So I just told him that don't worry, I will just ask the machine to design it automatically. So our goal is to just use formal methods with a little bit of machine learning. This is not LMs, it may disappoint some of you, but we're going to utilize formal methods to automatically design a controller with 3 key properties. First, it should be cross-layer. It needs to unify all the actions we talked before at the same control plane. What's more, because we use formal methods, so we want it to be probably performant. We need to make tail latency robust to environments adversarial behavior, which could include unpredictability of encoder output, fluctuating bandwidth, and jitter. Last but not the least, we also want it to be interpretable so that people can understand what the controller is doing and why. So here's our dream. We just want a very magical synthesis tool that just takes the word model that describes the adversary behavior of the environment and the performance objective, which is declarative, that specify how the controller should behave. Then the tool will either return the synthesized controller or the proof that no controller can achieve the objective under the word model. If the synthesis fails, we can just relax the word model or the performance objective and try again. I just casually said that we need a model of the word, but imagine what does this include. We need a model of the entire network, the entire video encoder, and the complex operating system. This is almost impossible. So our key idea is that most models are just trying to do too much. They are trying to predict the exact probability distribution of what will happen. Instead, if we just predict only the set of things that can happen, it is a much easier task. So we advocate for non-determinism, worst-case model instead of a stochastic or probabilistic one. They can be easily specified symbolic with logic, and also it can capture more of reality, just satisfy our goal of probably performant. So, but people may ask, because this is worst-case reasoning, we need to make the controller work, even if I'm adversarial or picking word behaviors from that side. Couldn't that be too pessimistic? We will show, however, that with the right choice of assumptions objectives, optimizing for the worst case will also optimize for the average case. And we will show this fact in the evaluation. So word model, let's go in the detail of it. It is composed of an encoder model and a network model. So let's model the video compressor first. In a static scene, like the Zoom call, each frame compresses well below the 40 kilobytes target bit rate. But in a high-quality movie, the actual bit rate is around the target bit rate with only very small variance. But in live action sports with constant movement, the encoder will frequently produce keyframes that overshoot the target bit rate very frequently. So modeling this with a probabilistic distribution is very hard. Instead, we will just use a simple non-deterministic model. The output bit rate is just the target bit rate plus or minus epsilon, where epsilon can be empirically determined for different video stream types. There are no distributional assumptions needed. So then let's talk about how to model the more complex behavior of the entire network. The network topology can be fairly complex. Each link has a different bandwidth and buffer size for the routers, and some routers can have shallow buffers. And also there are multi-user services competing for capacity. But luckily, from network calculus, the whole network can be viewed as a single first-in, first-out queue of a certain size, drained at a certain rate. However, this idealistic model cannot express common scenarios like multi-user service, RTS, CTS aggregation, or scheduling delays inherent in the operating system. Instead, we borrow the model of jittery link from old work, and it introduced an actual jitterbox that can arbitrarily delay packets by up to d seconds, and d can be empirically determined with no distributional assumptions needed. So now we can talk about the performance objective, what we expect our controller to behave. And our objective follows a lexicographic order. First, it must ensure there are no frame loss, and it also needs to make sure the latency deadline is bounded. And these are specified as safety properties. Then the controller needs to maximize QoE, quality of experience. It first needs to minimize the skipped frames for video smoothness. Then it needs to discover the network capacity so that it can maximize frame quality. And this can be specified as reachability or optimality objective. And this design somewhat explains why we can also optimize for the average case. So now let us uncover the magic synthesis engine. So essentially, the interaction between the environment and the controller can be formulated as a two-player game. The environment will present a state consistent with the model first. The controller then will pick an action. And the environment will then respond with a new state. Well, this alternation can continue unboundedly. And the controller can win if it can enforce the performance objective in every round, regardless of the environment's moves. A winning strategy for this game is exactly the controller we want. So concretely, our game is more complex than a standard formulation. It treats components of the video streaming system as a unified control plane, and the game is also partially observable. On the controller's turn, it selects the bit rate, sending rate, whether to skip the frame, all these actions. On the environment's turn, it will update the encoder output and network state, like delivered bytes and lost bytes. However, the environment also has latent states that the controller cannot observe or act on. To handle this, the controller maintains the belief set at each round, using past observations and actions to derive bounds on the latent states. These bounds are computed by a belief function obtained automatically through quantifier elimination. And with the game formulated, we can just use minimax, which can help us play the chess to find the winning action, accelerated by heuristics such as alpha-beta pruning and killer moves. Since we cannot run the game solver online, we will just use imitation learning to distill the strategy into a decision tree that can be executed directly at runtime. So for more detail, please go over the paper for them. And synthesis takes about 3 to 4 hours to produce this controller. It is difficult or even impossible for a human to come up with this algorithm. Even after the machine told us the solution and we understood it, we still cannot replicate it on our own. So now let's go to the evaluation section. First, we evaluate on our algorithm on the fixed link rate. The green line shows the maximum number of packets the controller can send without causing packet loss. It is updated based on past observations. And the red and blue box are the best to be sent. The first thing is that if the packets to send can be delivered without loss, like below the green line, then the controller will add FEC to probe for the bandwidth. More interestingly, if the frame returned by the encoder is smaller than requested, it can probe more aggressively. If, on the other hand, the encoder generates a K-frame and gives us more packets than we requested for, it will not add FEC at all and will not probe for the bandwidth, so that you can make sure every frame it sends meets its deadline. At some time, the rate we are sending at will exceed the network capacity. In that case, there will be network delay. We have to stop sending for 2 time units before we can stabilize into the steady state. And once we are in the steady state, we're going to send packets at every time step. The latency is now lower because we are in a predictable situation. Next, we pick a more complex scenario, the aggregation jitter environment. Sometimes the network delays the sending too much and latency budget is tight. So it will change the way of how to add FEC. It will tend to make the FEC block small so that it can be coded quickly when there's a loss. The second thing to notice is that when there's jitter in the network, the probe for network bandwidth does not always succeed. However, it will try to build up the no loss rate, and later it can probe more aggressively, has more chance to succeed. We then also can compare our algorithm with 3 other baselines on 6 real cellular traces. Syntra performs much better on tail latency, while are still comparable on the other 2 metrics, quality and frame rate. We believe the reason is that it can exploit some opportunities that only cross-layer design allows. So, takeaways, we designed a Syntra, which is a system that synthesizes cross-layer video streaming controllers from symbolic models and declarative performance objectives. It uses assumption-constrained worst-case models to capture the real-world behavior. It also uses formal methods to verify and synthesize the probability performance controllers under such models. And feel free to just scan the QR code to get access to our synthesizer and synthesized controller. And thanks, Arun.